You can see the point B is lying on this line having coordinates x1 and y1. So whenever we substitute it here, the equation takes the form. So at the point B having coordinates x1, y1, it takes the form y1 is equals to y0 plus x1 minus x0, x0 plus h by 2. And one more change I am going to make it here. In place of y11, I can put this value. So this now takes the form y0 plus h by 2 f of x0 and y0. And ultimately, the equation takes the form y0 plus, this is the length of the interval, and we have shown it by the letter h. So I can replace it by h. Inside this gives you f of x0 plus h by 2 y0 plus h by 2 f of x0 and y0. So you can see here, this is going to be your first approximation for the solution curve within the first interval of x0 and x1. Now similarly, if we proceed and we keep on changing the interval from x1 to x2 and onward. So for the interval number 2 of x1 to x2, according to this equation, we can write down directly y2 will be equals to y0 plus h times f of x1 plus h by 2. y0 will be replaced by y1 plus h by 2 f of x1 y1. And similarly, if we keep on doing the same procedure, same steps again and again, we can generalize it and we get ym plus 1 on the left side. On the right side of this will be y1 here, ym plus h f of xm plus h by 2, ym plus h by 2 f of xm and ym. So this becomes your the formula number 3, which is named as the modified Euler's formula. Okay. After this derivation of the formula, now you can see here in this formula, as I told you in the previous lecture, the importance of this formula is this formula can be used to solve the first order linear differential equations along with some initial condition. And here you can see that derivatives have been replaced by simple algebraic functions. Because derivatives are a bit difficult to tackle, that's why these numerical techniques are introduced to approximate the solutions for those problems which were perhaps difficult to solve. So here now we shall apply this formula of the modified Euler's method in order to solve some problem. I'm solving the same problem as I have done in the previous lecture, and then we shall be making comparison of the results with the previous two methods results. So you have to keep this formula in your mind. Now we are taking start solving the problem. The problem is the same problem. You are given a differential equation of the form 1 minus y along with the initial conditions of y0 equals to 0, and you have to find the solution within the range of 0 to 0.3 with an increment of 0.1. So here, whenever you make the comparison with the general equation, so we can write down here fxy is equals to 1 minus y. And this is the interval through which we have to move. The starting value is x0, which is 0, and we have to reach to this. So the increment is 0.1, so first break will be at x1, that is 0.1, x2, this is 0.2, and of course the last one x3. And corresponding values at x0, y0 is given from the initial condition, we can write it here. y1 you have to calculate, y2 similarly you have to calculate, and y3 we have to find it out. Now this is the whole picture for the given question. Okay, the next step is writing the formula. The formula for the modified Euler's method. The formula is still on the board. You have to just put it here, ym plus 1 ym plus h times f of xm plus h by 2 ym plus h by 2 and f of xm and ym. So this is the formula you have to use in order to approximate the solution for the given differential equation. Okay, now we proceed in such a way that we have to substitute this function for the outer function as well as for the inner function. These are the two functions, and first we replace the inner function with this. So the result takes the form ym plus h times f of xm plus h by 2 ym as it is, h by 2 as it is, and this part is replaced by this function. So this takes the form 1 minus ym. Now you can see here, this is the x coordinate of this function and this is the y coordinate of this function. And now we are going to use this function in place of this these coordinates of x and y. So the ultimate result takes the form h times. Now applying the function x coordinate, there is no x variable involved, so this is not going to be placed anywhere. The y will be replaced by this. So the result takes the form h times 1 by 1 minus y. Y is the y coordinate, which is ym plus h by 2 into 1 minus ym. Okay. So here we can see, we can place bracket here to separate them. Okay. After doing this, the next we can further simplify it. On further simplifying, you will be, after putting these values of h, which is 0.1 given in the question, and on simplifying, the ultimate result we get ym plus 1 is equals to ym plus 0.095 into 1 minus ym. So here you can see, after putting the values of h at two places and joining the like terms and simplifying, we get this. This is basically the recursive relation, and we can use it to find out the unknown values of y's. So we are now using this recursive relation, starting from m equals to 0. On the left side, this gives you y1, y0, 0.095, and 1 minus y0. And you know that y0 is 0, so we can replace it here. And on putting the values of y's and simplifying, you will be getting the ultimate result of 0.095. You can verify it of yourself. It's not very complicated. The next is taking m equals to 1. On the left side, this gives you y2. On the right side, it is y1 plus 0.095 into 1 minus y1. So y1 we have calculated. We can put it here and here. And simplifying, the net result will be obtaining is 0.180975. This is the second output. And the third output for m equals to 2 is y3 is equals to y2 plus 0.095, 1 minus y2, and again substituting the values of y2 from here, and on simplifying will give you 0.258782375, whatever it is.